Hey guys, Greaves here, right? Still, let's continue with modern physics. Okay, so what have we talked about so far, right, as far as modern physics is concerned? We talked about this weird thing about light, right? And light is this bundle of packages of waves, right? Really odd, actually, right? And by the way, right, we know that light has energy. Well, how do I know that? Well, it's getting nice out. All I need to do is stand outside and have the sun shine on me and I start to get warm, right? Why is that? Well, energy is being produced in the sun and, being transmitted to us, right? So I can find out the energy of these little packets, right, with a real simple equation, right? Energy of a photon, bundle package of waves, is directly related to the frequency, and I multiply that by Planck's constant, and I can get the energy, right? Well, don't forget, a wave has both a wavelength and frequency, right? So not only is it directly related to frequency, it's indirectly related to the wavelength, right? So here's one way to find the energy of these weird little particles, right, of light. But one thing that we do know, right, is that the energy of these particles are not continuous. We can't have anything that we want, right? The universe has already laid things out for us, meaning if I had a hydrogen atoms, right, that energy, right, that electron, right, is allowed to move up and down, right, in specific spots on that electron, like ground state, n equal 1, n equal 2, etc. Let me just get my diagram here. So here it is, right? And, right, the energy, right, that this atom, hydrogen, can absorb, right, or emit is quantized, right? So, for instance, going from 1 to 2, right, I take the difference, right? EI minus EF. If I went to 1 to 3, 3 to 4, etc. By the way, same deal with hydrogen, right? No big deal, right? Now, what's weird about it is hydrogen can only accept or what? Emit certain photons, right? Quantized. Mercury, it's also quantized, but it has different values of quantization, okay? It's the same concept. I get different photons out of hydrogen, right, than I would get out of mercury. Okay, so that's what we've looked at so far. Hopefully yesterday you played around with that little virtual lab, and I hope that, like I said, things are hard, us being far apart, right, but I hope we got a little bit out of that, okay? If not, it was just a little good to play around a little bit, okay? So what else? What's one of, right, coming to the end, right, of your physics course here at Mappin, right? Virtually, right? Right. Last thing. Well, believe it or not, it's Einstein's most famous equation, right, of E equals mc squared. So let's just take a look at the implications of this. If I could just, I'm going to look over, if I can get rid of the c squared, what does it say? Well, as a matter of fact, energy and mass are the same thing. Let me say that again. Energy and mass, the same thing. Analogy. Is water and ice the same thing? Sure it is. Water is just liquefied, right? Ice, or I should say ice is solid water, right? So it's an analogy, right? I like to say that matter is frozen energy. If I thaw the matter, I get energy. Really odd, right? So what's the implications of this? Well, we can get a lot of energy out of a small amount of matter. Like we can, like a nuclear power plant. Nuclear power plants produce a lot of energy, right? And they do it quite efficiently with not a lot of mass. Well, that's good, but it's also bad. Why is it bad? Because the byproduct of this reaction is still radioactive, right? So we got to get rid of it somewhere, right? So there's issues with that, just like anything else, right? So let's take a look at Einstein's very, very famous equation. Okay, so what is his famous equation? And probably the most famous equation of all time. Energy, E equals mc squared, where E is what? Energy, right? By the way, this is in joules. M is going to be, let me just say, is what? Mass. That's kilograms. C is obviously what? That's equals speed of light, 3 times 10 to the 8th meters per second. Okay? So let's take something really, really quite simple. Let's suppose, right, I could take, and by the way, we can't do this, right? Let's suppose I take 1 kilogram of matter. I don't know what it is. Who knows? Some magic material that I can convert totally into energy, which it can't, right? So let's see if I can take 1 kilogram of mass and I can convert that, let's say convert to what? Energy. How much energy would I have? All right, and Einstein's equation tells me E is equal to mc squared. So what do I have? 1 kilogram, 3 times 10 to the 8th meters per second squared. Okay, by the way, this is 1, and we are going to square things, right? So this is going to be 9 times 10 to the 16 joules. Wow. The implications. Now look, we cannot convert 1 kilogram of mass to energy. But, right, if we did, we get a staggering amount of energy. I don't know if it's true anymore, but I did hear at one particular point that the energy of like New York City, right, 1 kilogram of mass, right, if I can convert it totally, would power New York City for a day. That's pretty impressive, right? That's not a lot of stuff, right? We can turn on all the lights, do whatever needs to happen in New York City for a day. Anyway, powerful stuff, right? So that is one way to look at Einstein's famous energy equation. I'm going to go into something a little bit more advanced, right? And we're going to talk about this more, right, in the next day, which would be Thursday, okay? So physics, right, modern physics does get a little bit strange. So ready? Let's suppose I had a proton. Here's another way, right, to look at Einstein's equation. Let's suppose I take that proton and I have it zip off in this direction, okay? I'm going to have something called an antiproton. Don't get upset with this, or confused, I should say, with me saying it's an antiproton. I'm going to discuss this in detail tomorrow, okay, about matter and antimatter. And yes, it's not science fiction. Antimatter does exist, okay? So what would happen? What would happen if I get a proton and an antiproton meet? Well, if you guys seen all those science fiction movies, you are correct, right? What's going to happen is a proton and an antiproton, when they meet, they're going to annihilate each other. Let's make a big boom. What's going to happen? They are going to annihilate each other and produce pure energy, right? So let's ask this question. How much energy, right, would a proton and an antiproton produce if they were to meet up? All right, energy is equal to mc squared. All right, well, what's the mass of a proton? Okay, so let me go to the front page of the reference table. Mass. Okay, rest mass of an electron. Nope, rest mass. There we go. Rest mass of the proton. 1.67 times 10 to the negative 17th. All right, hold on a second. Let me just write that down. 1.67 times 10 to the negative 27 kilograms. That's the mass of a proton. What you don't know, and I'm just going to tell you now, and you'll know a little bit more tomorrow, the mass of an antiproton is exactly the same as the mass of the proton. Like I said, we're going to get into this later. I just want you to get the math. The only thing different about these two is, oddly enough, is that they have opposite signs, right? Well, anyway, so I really have how many particles right here? Well, I have a proton with this mass, and I have an antiproton with that mass. So I'm going to have 2 protons, 1.67 times 10 to the negative 27 kilograms, times what? 3 times 10 to the 8th meters per second squared. All right, let's get my handy dandy calculator. Let's do this one first. 3 second E, 8 squared, right, good, times what? 1.67 second E minus 27 times 2 equals, booyah, right? So I get 3.006 times 10 to the minus 10 joules, right? So, well, do I get energy? I do. Do I get a lot of energy? I don't. Why don't I get a lot of energy? Because I didn't convert a lot of mass, right? So anyway, here's another way to look at Einstein's famous equation of E equals mc squared. Now really, we're not going to get into it in this class, right? But really what happens in these, nuclear reactors is that energy, or I should say mass, at the nucleus level is being changed or converted back and forth to energy all the time. And say I had a nuclear bomb, really, what happens is by releasing, right, the energy right there, right, by ripping atoms apart, right, what we do is release tremendous amounts of energy. Okay, so this is Einstein's E equals mc squared. I'll send a couple of problems off on test wizards, right? Shouldn't be a big deal. All right, guys, see you later.